We finally proved that the Hausdorff dimension of Heisenberg group is 4, but be patient, we actually end up proving a lot more. The story started by using only basic observations to prove that only at dimension 4 could the Hausdorff dimension be non-trivial. Namely, we used only left invariance of L3 of the Carnoy-Carathédry distance, and also facts that we had proven about the dilation and how it behaves under these two operations to show that H alpha is a constant multiple of the Lebesgue measure. But this constant is either 0 or infinity unless alpha equals 4. However, from similar basic observation, I was unable to show that indeed 4 is the Hausdorff dimension and that it is finite and positive for, say, unit ball. I'm still looking for some magical way to prove this, but meanwhile I remembered that there is actually a more general fact from which we can prove that dimension is 4 and indeed also prove that the Hausdorff 4 measure is what is called Alford's regular, which I will explain in a second. The theorem in any metric space, this is not specific to Heisenberg group or sub-Riemannian manifolds or anything. The theorem says that if you have some metric space and then there is a measure on that, it's a Borel measure, the balls are measurable, and we happen to have a constant q, the more important constant, which is going to be the dimension, and then there is a control constant c such that the measure of a ball of radius r, no matter where it is located for every x, is comparable to qth power of r. So it's basically measure of a ball of radius r is just r to the power q, except we probably have not equality but by Lipschitz similarity. If we happen to have a measure with these properties, the measure a priori having nothing to do with diameters or Hausdorff measure, it turns out that in this case, in fact, the Hausdorff Q measure behaves similarly. There is a different constant. By this we mean there's a different constant so that this is less than c prime r to the power q and bigger than 1 over c prime r to the power q. That means the measure, Hausdorff measure, behaves very similar to this measure mu. And because this becomes positive and finite, it shows that the dimension of the balls is q. This is a very well-known theorem. I haven't seen it be attributed to any particular person or author, which shows that it is so well-known and part of the folklore of metric geometry. Let me give you the specifics of this corollary. So we have seen that L3 has these properties. So you take a ball at x and of radius r. Because Lebesgue measure L3 is invariant under left translation, the determinant of the left translation operator was 1 everywhere, we can transfer the ball to 0. The radius wouldn't change because the distances are left invariant. And then ball of 0r is dilation of the ball, the unit ball, by factor r, because dilation shrinks the diameter and the distances by exactly r multiplication. And then we have seen that L3 of dilation is r to the 4 of that, because the determinant of the dilation operator, which was a linear map from R3 to R3, was r to the 4. So it shows that a ball centered no matter where of radius r will have measure equal to r to the 4 times a constant. So this will not depend on r or x. It's just some number which is not 0 or infinity. It's just L3 measure of some compact bounded set, and open, containing an open set. So from this, we actually see that the assumptions of the theorem for measure mu hold with q equal 4 and c in fact equal 1. We have more than just the assumptions which said that you want comparability to the r to the 4. We have actually exact equality to r to the 4. In fact, well, maybe mu divided by this measure, this particular number probably is what I mean has the property with c equal 1. Yes. Anyway, now that the assumptions of the theorem hold, the claim of the theorem says that H4 is comparable to r to the 4, in particular positive and finite for every x and every r positive. And this means that the Hausdorff measure of every open ball is equal to 4. And since H1 is a countable union of these, the whole thing also has Hausdorff dimension equal to 4. So this is an immediate corollary of this well-known and very nice theorem from metric geometry, whose proof by no means is too complicated. It's a very deep result, it's a very important result, but once you know it is true, once someone gives you this result, the proof should follow from definitions. Because you know nothing about this measure, that is an indication that the proof must be easy. Only use definition of Hausdorff measure and some covering arguments. I don't want to get into details of this, at least in this lecture, but you could find the proof of this, for example, in Professor Ledonne's notes that I have mentioned before, which has a lot more about sub-Riemannian geometry and Heisenberg groups in general. So his notes has a nice proof of this theorem. You can also find it in probably some books. Okay, if you have any questions and if you don't find this proof of Hausdorff dimension of H1 convincing enough, let me know in the comments. And thanks for watching.